Hello and welcome to part 4 of module 18 in our C language series. In today's session, we're going to focus on the hashing approach to sparse arrays. And talking about hashing, it's a technique that is not only used with sparse arrays, it's also used in the encryption and decryption of passwords, for example, as well as to allow for faster access to disk files. But today we're going to limit our discussion on hashing to its use in the context of sparse arrays. And in that context, hashing is the process of extracting or deriving the index of an array element using the information stored there. What is a hash? A hash is nothing but the index so derived. Right? So what happens is we use a kind of an algorithm or a hashing method as it is called in order to derive the index. Now you may recall that in the last session in our discussion on pointer arrays or the pointer array approach to sparse arrays, I should say, we did use an algorithm in order to derive the index for each element in the pointer array. And that in fact is a hashing method which is called direct indexing. With direct indexing, each index is unique, which means that each index or key or hash maps onto one and only one array location. But this is rare when we're using hashing. So let's now look at how to generalize hashing to provide for more flexibility. And keeping with the same example, which is our spreadsheet example, we know that in any event, in the most demanding environment, not every cell on a spreadsheet is used. And so we can decide on a percentage or a constant which would relate to the percentage of a spreadsheet that will be used. For the purpose of our discussion, we're going to keep that at a 10%. Considering that we have 2,600 locations in our logical array, and we're going to assume that only 10% of those are going to be actually used, then our physical array would consist of 260 locations. But if the physical array consists of 260 locations and our logical array consists of 2,600 locations, certain questions will arise, like how do the logical array locations get mapped onto the smaller physical array, or how are the locations accessed if we have more than one logical location mapping onto one physical location? What happens if and when the physical array of 260 locations is all used up, right? All locations are full. To answer those questions, let's understand how hashing works. The input to the hashing method in our case would be the cell name and the formula. We would take that cell name and use it to derive the index for the physical array. We would then divide that index by 10 because of our 10% assumption. We would then check the location in the physical array at that particular index to see if it is free. If it is free, then we go ahead and store the logical index and its value at the location in the physical array. What happens if the location is not free? What we have then on our hands is what is called a hash collision, which means more than one logical location map onto the same physical location. How do we resolve this? We resolve it by creating a collision list for the location in the physical array. Now the collision list is nothing but a linked list. Right, so let's look at a hashing example. If we have entries like this, their cell names A1, A2, A3, and this is our physical array, you can see them already placed there in the free locations. If our next cell name is B1 and using the hashing method, it maps onto the same location as A1, then we have a hash collision. And so we create that collision list and you can see A1 points to B1. Similarly, if we have B2 coming in and B2 hashes or maps onto the same location as A2, then we have a hash collision again, and we can create a collision list with A2 pointing to B2. Similarly, if we have C1 and it maps onto the same location as A1, Then we can have B1 pointing to C1, and you can see how the linked list is growing there, right? Finally, we have C3 mapping onto the same location as A3. And again, we have a hash collision, so we have a collision list there. It's important to remember that the length of every collision list would be 0 until a collision occurs. Now to do a recap of the procedure, the user of the spreadsheet enters a formula for the cell. The cell location is used to produce an index or a hash into the smaller physical array, right? This index is then divided by 10, and we check the location in the physical array to see if it is free. If it is, then we store the logical index and its value there. If not, we create a collision list to accommodate that entry. Remember that there will be a separate collision list for each entry in the primary or the physical array. And the length of each collision list will always be 0 until and unless a collision occurs. Now, if we have 2600 locations in the logical array and we have 260 in the physical array, how many of the logical locations will map onto the same physical location or onto one physical location? And if you do the math, that would be 10 logical locations mapping onto the same physical location. Now let's go ahead and write some code. So write a program to implement the hashing approach to sparse arrays. Let's now go to code blocks and we'd start a new file. And we start with hashtag include stdio.h and then hashtag include stdlib.h and hashtag include string.h, and we have a hash define here. We're going to call that max. That's going to be 260. Now we have our structure. So struct h type, and the structure members are going to be int index and then char cell name of 9 bytes, int val, and we have a pointer. So struct h type star next. This is to help with the collision list. We're going to call this primary r, and that's going to be of max number of structures. So it's going to be an array of structures. The functions we'll have are init. We've got to initialize all the structures in this array. And then we have store data, which is going to take as parameters char star cell name and int v, right, for val. Then we have a link store function, and this is going to take struct h type star h, let's call it that, and struct h type star start, right? Then we have a function that's returning an integer. That's the find function, which is going to locate a cell and return the value stored there. So char star cell name is going to be the parameter. We have a delete cell function, so void delete cell, and that's going to take again char star cell name as parameter. We have void printar, right? There's no parameters there, and we need a pointer to the structure. That's struct h type star start, right? Now our main function, And within this function, we'll have char locate name and cname, both of 9 bytes. We're going to use these to get input from the user. Right? Then we have int, store val, and found. Store val again for input from the user. Found will be used to catch the return value of the find function. Right? We have start being initialized to null. After this, we will call the init function to initialize the array. Right? Then we have a while loop. This is an infinite or eternal loop. And within this, we'll first ask for the cell name. So printf enter cell name. And then scanf comma cname. Right? flush stdin. Now we check if cname of 0 is equal to a 0. Then we break out of the while loop. Right? Otherwise, we ask for the value. So in this program, we're just entering numbers. You can change that later on after the session if you want to put in a formula. And then scanf %d comma ampersand store val. Right? flush stdin. Right? Then we call store data, sending in cell name, that's cname, and store val. Right? So those arguments will go into the function. Now, out of this while loop, we will call print r. And then the next thing is to ask the user for the cell to find. So enter cell to locate. And then scanf %s comma locate name. Right? And then flush stdin. Now using locate name, we'll call the find function and we'll use found to catch the return value. So found equal to find and pass in locate name. Right? Then we check if found is not equal to a 0, then we don't need a bracket actually. We can just put in a printf statement here. Printf found value is %d comma found. Right? Else printf not found. Right? Now we will call the delete function. So we need to ask the user for which cell they want to delete. So enter cell to delete. And scanf %s comma cell to locate or locate name. That's what we've called it. We're going to use that same variable. Right? flush stdin. And then we'll call delete cell, passing in locate name. Right? Once the cell is deleted, we call print r again, just to make sure that in the output we do not get that cell. Right? Now we need to end the program, so exit 0. This completes our main function. Right? The next function we write is the init function. So void init, and within this function we'll have register int I, and then for I equal to 0, I less than max, I plus plus. And within this loop, we'll initialize all the structures in the array. So primary ar of I dot index equal to -1. And then primary ar of I dot next is equal to null. And primary ar of I dot val is equal to 0. Okay, that completes the init function. The next function we write is the store data function. So void store data, and the parameters are char star cell name and int v. Now within this function, we'll first have some variables, integer type each and log for location. We have struct each type star ptr, right? And now we have our hashing method. We're using the same method we used with the pointer array approach. So that's star cell name minus a, right? And then loc or loc plus equal to a to I, that's ASCII to integer of ampersand cell name of 1, right, minus 1 multiplied by 26, right? Then we have to now divide log by 10, right, following the same procedure we discussed earlier. Now we put in a printf statement to observe these values. So printf h, that's going to be a %d. Then we have log, that's going to be %d. And then we have primary ar of h dot index. And again, that's going to be %d, comma h, comma log, comma primary ar of h dot index. Right, this is just for us to observe how the program is running, right, and the values of these variables. Right, now after this, if h is greater than or equal to max, right, then we printf cell out of bounds and return, right? Out of this, if block, we check if primary array of h dot index is equal to a -1, which means the location is free, or primary ar of h dot index is equal to log. Then we proceed to store the values, right? So primary r of h dot index is equal to LOC. And then primary r of h dot val is equal to v. Now we will use memcpy. So memcpy, destination is primary r of h dot cell name. The source is cell name. Number of characters is strlen of cell name plus 1. Right? And then return. Okay. If not, as in if this condition is not met, then what we need to do is, of course, create that collision list, because now we have the situation of a hash collision, right? So ptr equal to malloc size of struct h type, right? And then check if malloc returns a null. So if not ptr, then printf out of memory and exit 1. Otherwise, we say ptr index equal to log ptr arrow val equal to v, right? And memcpy, the destination will be ptr arrow cell name, right? The source will be cell name, and the number of characters will be strlen of cell name plus 1. Right? I hope you're with me. Then we check if start is a null, right? We're creating the collision list. So if start is a null, then start equal to ptr. And we call link store, right? Sending in ptr and ampersand, that's the address of primary r of h, that's the address of that structure, right, in the array. That completes our store data function, right? Now let's write the code for link store. So void link store, and the parameters are struct h type star h and struct h type star start. Now within this function, we have a pointer, so struct h type star old, right? And we're going to say old equal to start, and while start is not equal to null. Within that while loop, we'll have old equal to start and start equal to start next, right? Out of this loop, we'll say old next equal to h and h next equal to null. Okay. That completes our link store function. We'll now have our find function that's taking as parameter char star cell name. Within this function, we have int h, comma log, and struct h type star p, right? Then log equal to star cell name minus a, and then log plus equal to a to I of ampersand cell name of 1 minus 1 multiplied by 26, right? And then h equal to log divided by 10. Then we say if primary r of h dot index is equal to log, which means we have a match, then we can return the value. So return primary r of h dot value, right? Else p, that's the pointer, equal to primary r of h dot next, right? And then while p is not equal to a null, within that while loop, we check if p arrow index equal to log, then return p arrow value, right? Val otherwise p equal to p arrow next, right? Now if it is not found at all, then we can just return 0. Okay, now we write a print array function. So void print array, no parameters coming in there, and within the print array function we have int counter comma log, right? And we need a pointer struct h type star temp to help us to print out any collision lists if there are, right? So for counter equal to 0, counter less than max, counter plus plus. Within the for loop, we check if primary r of counter dot index is not equal to a minus or a -1, which means we have something to print out in that location. We can go ahead and print the details. So printf index and %d \n comma primary r of counter dot index, right? We'll also print the cell name. So printf cell name, right? And then %s \n comma primary r of counter dot cell name. Okay, also the value. So printf value %d \n comma primary r of counter dot value. Now we need to check if next is null, right? Or if there is a collision list. So if primary r of h dot next is not equal to a null, that is, then here we'll say temp equal to primary r of h dot next, right? And then while temp is not equal to a null, within this loop we'll check if star temp dot index, we need another bracket there, dot index not equal to a minus or a -1, then we can print the details. So printf index %d \n, comma temp arrow index, and printf cell name %s \n, comma temp arrow cell name. Similarly, printf value %d \n, comma temp arrow value, or val as it is called, and then we've got to say temp equal to temp next, right? So we do that here, temp equal to temp next, and then of course this loop will repeat, right? So this completes our printr function. Okay, now we will write the delete cell function. So void delete cell, and that's going to bring in the parameter char star cell name. Within this function we'll have int h comma lock and struct h type star p and star temp. Okay, and then we have lock equal to star cell name minus a, that's our hashing algorithm, and lock plus equal to a to I of ampersand cell name of 1, right, -1 multiplied by 26, right? H equal to log divided by 10, and then we check if primary r of h dot index is equal to log, which means we found the cell we want to delete. Now we need to check if there's a collision list there. So if we'll check if there's not, so if not, primary r of h dot next, which means that's a null, right? So primary r of h dot index, we'll reinitialize that to -1, right? And then we'll have primary r of h dot val equal to 0. That's all. And then we'll return. Okay. Else, which means we do have a collision list, then we will use temp equal to primary r of each dot next, right? And then we say primary r of each dot index equal to temp, or rather star temp dot index, right? So you know what we're doing here. We're essentially preserving the collision list, the link list, if you like, right? Then mem cpy primary r of each dot cell name, that's our destination, comma, temp, or rather star temp dot cell name, and number of characters is strlen of star temp dot cell name, right, plus 1. Okay, then primary r of each dot next will be equal to temp next, or temp arrow next, and primary r of each dot val is equal to star temp dot val, right? Then we free temp, right? So we free that pointer and return, right? So we preserved the chain or the list. Else, that's for this if now, which means we have not found that match. Then we say p equal to primary r of h dot next, right? And then while p, and here we check if p arrow index equal to lock, then we check again if p arrow next, right, which means there's a collision list. If there is, then temp equal to star p dot next, right, and then star p dot index equal to star temp dot index, and mem cpy, the destination is star p dot cell name, right, comma, star temp dot cell name, right, comma, strlen of star temp dot cell name plus 1, right? Then p arrow next equal to temp arrow next, and then star p dot val equal to star temp dot var, right? And then of course free temp, right? If we do not have that collision list else, then we can just reinitialize star p dot index equal to -1 and star p dot val equal to 0. Now we need to move along in this list, right? So here we say p equal to p next, right? So this completes our delete function. Let's run this code now and see the results. We have an error, H undeclared. This should be in effect counter, not H. So that's the mistake. Right, so just replace this as well. Okay, so let's run that again. Right, let's enter some data. So I'm going to put in C45 and we have a value, let's say 456. Now you can see the index has got -1, which means that the location is free, right? Enter D45, enter some value. Now you can see we have an index there, right? Because this H is, you can see that hash is the same. So what this is doing now is creating that collision list. Okay, enter another cell name, let's say Z45. Let's enter a value and you can see again that's -1. This is a different hash value, right? Enter Y45 and enter some value there. And now you can see that this hash value is again the same, right? And so this is now creating that collision list. You can see there's an index there, right? Which is of course lock. Okay, now let's put in some other cells. Let's say A1. Let's put in a value. And again, the index is -1. Put in B1 and put in a value. And you can see the hash value is the same. So again, that's a collision list being created. C1, let's see. And again, the hash value is the same. Enter B2, right? And now the hash value is different. So index is of course -1. Enter D2 and some value. And again, we have the same hash value. So I hope you've understood how this works now. I'm going to put in a 0 and we have all of them printed out, right? Enter cell now to locate. Let's say C1 and you can see it's printed out that value 543. Enter cell to delete, right? Let's say D2. Okay, this is not printing out anything, so we've got to check why that is. So here we're calling delete cell, passing in locate name, printar, we should have the brackets there. And that's why it's not running. So now let's enter some data again. And before that, let's put in a \n as well because the screen looks a little untidy. So after that printf statement, that's here, we'll just put in a backslash n. Okay, so that will make the screen look neater. Now let's enter some values. Let's say D34. Let's enter some value there. You can see the index is -1, the hash value is 86. Enter an F34, enter a value, and again you get the same hash value. So now the index contains lock, right? Enter Z34 and enter some value, and again the index is -1, hash value is 88. Enter W34 and enter a value, and you can see again that hash value is the same. It already contains an index, right? So it's creating that collision list, right? Now let's enter, let's say D1, and let's put in some value there. Again we have index -1, enter B1 and enter some value, and now we have the same hash value, so a collision list is created, right? Enter, let's say A1 and put in some value, and again we have the same hash value, so that's a collision list. Enter B2, put in some value, right? And we have index -1, and enter D2, enter some value, and again we have the same hash value. So I hope you understand how this works. Put in 0, and we have all of them printed out, right? Now enter cell to locate, let's say D34, and we have the value printed out there. Enter cell to delete, let's say B2, and now you can see that B2 does not appear in the printout, right? So you can play around with this program, right? And of course understand better how it works. Now moving on. Let's now analyze the hashing approach. The best case would be if we had a replication of direct indexing wherein each physical index is unique, access times approximate that of direct indexing. There are no collision lists because each index is unique and all lookups are direct accesses, but this is very rare because we would have to evenly spread out the logical indexes or indices or locations, if you like, in the logical space or the logical array. The worst case would be if our hashing method or hashing scheme degenerated into a linked list, and this would happen if all logical locations mapped onto the same physical location. Again, this is very rare. The average case would be if the hash method could access any specific element in the time taken to use a direct index divided by some constant, for us that is 10, and the average case is the one that happens most commonly, right? Important to remember that when we use hashing, we need to avoid long collision lists. Now let's talk about how we decide on which approach to use. Do we use a linked list approach, the binary tree approach, the hashing approach, or the pointer array approach? There are two factors we need to consider: memory efficiency and execution speed. Let's talk about memory efficiency first. For that, we'll ask the question, is the array very sparse? Meaning, do most of the elements have a 0 value? If the answer to that is yes, then we can just use linked lists or binary trees because they are the most memory efficient, considering that they will only allocate memory to the elements that are needed or used, right? What about the pointer array approach? We know that with the pointer array approach, right, we would need that entire pointer array to reside in memory with one pointer for each logical location, right? And we also need to have space for the application itself. So that's not memory efficient when compared with linked lists or binary trees. What about hashing? So hashing lies somewhere between the pointer array approach and the binary tree and linked list approach. Why? Because remember, we do need a physical array when we use the hashing method. But of course, that array is going to be much smaller than the pointer array, right? But because we need that array, it's definitely going to be less memory efficient than the linked list or binary tree. What happens if the array is not very sparse? In that case, we will just go ahead and use the pointer array approach. Why? Consider this. If we have a 1000 element array and we use a binary tree or the linked list approach, remember we would need 2 pointers. And if each pointer takes 2 bytes, that's 4000 bytes. With the pointer array approach, we would use 1 pointer. That would mean just 2000 bytes. So that's saving of 2000 bytes. When compared with the hashing method and considering the array is almost full, we would actually waste more memory with hashing. And therefore, the pointer array approach is the most memory efficient. Now, talking about execution speed, the fastest approach is the pointer array approach. It allows for direct access. It has that capability. So that if we use a simple method like we did in the last session, then it would be as if we are accessing a normal array, right? The linked list is the slowest approach because we are using a linear search. The binary tree approach would be faster than the linked list approach, of course, because we're using the binary search, but it would never be as fast as the pointer array approach, right? Because again, the pointer array approach provides for direct access. The hashing approach could beat the binary tree approach if we had a good hashing algorithm, but again could never be as fast as the pointer array approach. So the rule of thumb is use the pointer array approach for fastest access times or fastest execution speed. But if memory usage is critical, then use binary trees or linked lists. Right? This ends our session for today as well as the module. In the next module, we talk about parsing, which is the backbone of compilers and interpreters. So till the next session, take care, stay safe. Bye.